This is tutorial 4B question 5B of Laplace transform. We extend the previous question of 5A with input equals to e minus 0.3t cosine 2t. The difference is that now we're using cosine 2t versus the single exponential in the previous example. Actually, there is no difference. The reason being that we can write the the cosine 2t as the sum of two complex exponential. So let us call this sigma and let us call this omega naught. And therefore now we have converted the e minus 0.3t cosine 2t into this expression over here. Now let's study this expression carefully. E sigma 0t multiplied by e j omega naught t plus e minus j omega naught t divided by 2. So this is the cosine 2t, and therefore now we understand that actually this half and this half came from this expression over here through the Euler's formula. Now what about S naught? Well, if we consider this, you will realize that there are two S naught. One is S naught due to sigma naught plus j omega naught for the first term, and the second term is actually sigma naught minus j omega naught. So therefore we actually have two expressions to represent the decaying cosine. Now because the system is linear, therefore we can apply the system onto these two signals separately, and we can break this response into this way. Again, using the principle of linearity, we can bring the constant half out, applying the system onto individual signal, and therefore this is the final output y of t. We have already done this guy. What about the complex exponential part? E s naught star t. What is star t? Well, remember that if S naught is equals to sigma naught plus j omega naught, S naught star, the typical expression is sigma naught minus j omega naught, the complex conjugate of the S naught. What you realize is this thing: the system operating on Es naught t will get Hs naught, and the system operating on Es naught t will get Hs naught star. Now what you will see later on, if you apply that, is that this would have a gain of, for example, Aej omega or Aej theta. For this one, it will be Ae minus j theta is complex conjugate on the face. The gain, the magnitude is the same. Sometimes it's written as, using this notation, the absolute value of this Hs naught, which is the magnitude gain, and then this is the phase theta. So sometimes you will also write it as A theta or Aej theta. So we like to write in the polar or the complex exponential form because it explicitly shows the magnitude and the phase that will be introduced to Es naught t. Alright, let us find the gain h of S naught. What is S naught? S naught is minus 0.3. So we see minus 0.3 here for sigma, and j plus 2 for omega naught. So we substitute this. This is sigma naught plus j omega naught, and we'll substitute into the HFS. We'll get this value in rectangle form, and we'll convert it into the polar notation. So again, this is A theta. So this is A here, or the magnitude, and theta is the phase. We would substitute this value into the final equation simply by multiplying by A. This is the original, e minus 0.3t, cosine 2t, the original omega, and this is the phase that is introduced. So again, it shows that the output will become smaller from 1 to times 0.68, and it will be introduced a phase of minus 1.166 radian. This is the expression. So with that, I'll use a supplementary slide to introduce why this expression comes out. Thank you.